I will go to the third lecture of week 8, and in this lecture we will put to use our understanding of Miller indices and distance between lattice planes in order to explain X-ray diffraction. Okay. So I will introduce X-ray diffraction, show how you can relate the X-ray diffraction to the Miller indices and the distance between planes, and then also look at try to talk a little bit about the reciprocal lattice. Okay. So, week 8 lecture 3 will be X-ray diffraction, Bragg's law and reciprocal lattice. So, let us talk in general about X-ray scattering and interference. Okay. Now, I will later on describe in detail how X-rays are generated, but for now let me just mention that X-ray is some ray, okay, of some wavelength, okay, and this is your X-ray, okay, and it is traveling in some direction. Okay. So, this is my X-ray, it is some beam, X-ray is some beam of electromagnetic radiation that is traveling in some direction, and now interesting things happen when it interacts with atoms. When it interacts with atoms, okay, so this is an atom, okay, it basically interacts with the electrons in the atom and then it gets scattered in some direction. Okay. Now, typically it will get scattered in several directions, but there is a scattering intensity which says that in certain directions the scattering will be the largest. Okay. So, now if there are several atoms, okay, then each of them will scatter X-rays. Okay. So, each of them will scatter X-rays, and actually I should emphasize that they are also scattered in other directions. Okay. They are not only scattered in one direction, they are scattered in several directions. Okay. And X-rays are electromagnetic radiations that interact with the electron density of atoms. So, I will just emphasize this part, that X-rays are electromagnetic radiation okay, and they interact with electron density. Field of atoms. Okay. And what we mean by electron density field is really the spatially varying electron density. So, whatever the structure of this electron density is, okay, around an atom, it is going to interact with that. So, if you have a d orbital, it will have some structure, okay, some electron density, some spatially varying electron density, and this X-ray is going to interact with that. So, whatever the electron density is around the atom, it will interact with that, okay, and it gets scattered in all directions. Okay, but the scattering intensity is typically larger in certain directions than others. Okay. So, the scattering intensity varies with direction. Now, so what we see is that now if you look at some faraway point, okay, let's say you look at this point, Okay. Now, this point is getting X-rays that are scattered by different atoms. So, it is getting an X-ray, let us say it is getting an X-ray scattered by this atom, by this atom. Okay. Maybe there is some X-ray that is being scattered by this atom that is also interfering. So, there are lot of X-rays coming due to scattering from different atoms at any point. So, many X-rays and so the question is there constructive or destructive interference? Okay, and so if there is there is interference of all these waves, and interference can be constructive or destructive. Okay. So, basically at every point you will see a different pattern of X-rays. Okay. So, this is the basic idea of X-ray scattering and interference, and now what we are going to see is how the underlying structure of the so obviously whether it is constructive or destructive depends on how the atoms are spaced with respect to each other. Okay, it depends on the relative distance and the relative positions of the atoms. Okay. So, now let us look at Bragg's scattering law, which is actually a hugely simplified version. Okay. It is a very simple result, and what that says is that this scattering of X-rays by all atoms can be imagined in the following way. Okay. So, what it says is that we can imagine X-ray scattering as effectively reflection about lattice planes. Okay. So, what the idea is that you can take this picture of X-ray scattering and think of it as effectively as a reflection about lattice planes. Okay. Now, obviously you do not really have reflections. I mean, what you have is fairly, you can see that scattering is fairly complicated process, and scattering is of individual atoms, not of planes. However, you can look at X-ray scattering. Okay. So, the at least as far as the interference process is concerned, you can imagine X-ray scattering effectively as a reflection about lattice planes. So, what this allows you to do is to look at this family of lattice planes. Okay. And now imagine that that if you have an incident X-ray beam. Okay, let me use a different color. If you had an incident X-ray beam, okay, now you can imagine that this will be reflected of this. Okay. So, therefore, if this angle is theta, then it will be reflected in such a way that this angle is also theta. Okay. And now these are lattice planes. Okay. And you can imagine, so Bragg's scattering law can be derived using this picture, that X-rays these are X-rays are actually getting reflected of lattice planes. Okay. And so, if you take another parallel X-ray beam, So, these two are the incident beams and these are the reflected beams. Okay. And what the idea is that there is going to be some interference here. If you put a detector here, okay, then you have to see whether these two beams interfere constructively or destructively at the detector. Okay. And the condition for constructive interference is given by Bragg's law, which is given by n lambda equal to 2 d sin theta. Okay. This is the very well known Bragg's law, which I am sure all of you have seen before. Okay. What is important to emphasize is that actually the interaction of X-rays with atoms is much more complicated than simple reflection of planes, but effectively if you do the entire calculation, if you do the entire scattering theory, okay, it's actually a fairly complicated quantum mechanical theory. The result that you get is just the same as this simple Bragg's scattering law. Okay. And I will not be doing this, I will not be trying to derive this, but what is interesting is that this quantity d that appears is the distance between lattice planes. Okay. So we see immediately that that this distance between lattice planes that we calculated in the last lecture is something that appears in Bragg's scattering law. Okay. Now, what is this distance between lattice planes? So, we know how to relate d is related to HKL ABC alpha beta gamma. So, if you know ABC, alpha, beta, gamma and HKL, you can calculate the distance between lattice planes. Okay. So, this is the basic idea of X-ray diffraction, that you have an incident beam, you have a reflected beam, and you can calculate the condition for constructive interference. Okay. And it is only when when there is constructive interference, you will see a maximum, okay, at the detector, and in that case you will have this Bragg condition. Okay. We will discuss this in more detail as we go on, but I just wanted to introduce the Bragg scattering law. Okay. Now, a slightly different way to look at X-ray diffraction, okay, is to do the following. Okay. If you have a travelling wave, okay, if you have a travelling wave in one dimension, this is travelling in this direction. Okay. So it is a wave that keeps moving with time. Okay. Now, so this wave has a momentum. It has a momentum of k, okay, and or if it has a momentum p, okay, then you can write its wave function. Okay. So, the wave function for a travelling wave in one dimension. So, this is 1D. Okay. Psi of x you can write as I will just put a constant, and I can write e to the I p by h cross x. Okay. This is a wave that is travelling with momentum of p in the x direction. Okay. So, this is a travelling wave in one dimension. Now, if you had in 3D, okay, before I go to 3D, this quantity p by h cross is written as wave vector I k x. So, k equal to wave vector. Okay, this is again related to the de Broglie hypothesis that wave has a momentum p, okay, and p by h cross will be what is called a wave vector. Okay. Wave vector is basically, you can think of it as 2 pi by lambda. Okay, lambda is the wavelength. Okay. Now, what happens in 3D? In 3D, you have k goes to k vector. This is k x I plus k y j plus k z k. Okay, so now k becomes a vector, and now instead of x you have r, which is x I plus y j plus z k. Okay, so instead of x you have r. Okay, and now your wave function psi is a function of r. Okay, so that this is a travelling wave in 3 dimensions. Okay, and this is given by some constant times e to the I k dot r. Okay, so it is a k dot r, that is same as a e to the I times k x x plus k y y plus k z z. Okay, so this is the travelling wave in 3 dimensions, and this is an equation of a travelling wave in 3 dimensions, and this is I haven't explicitly put time. Okay, but you know that you can calculate the momentum. Okay, the momentum will be equal to h cross k. Okay, you can work it out. Okay, momentum you can work it out by using minus I h cross dou psi by gradient of psi cross k vector. So, minus I h cross gradient of psi. Okay, so if psi has this form, okay, minus I h cross gradient of psi. Now, the grade this is equal to the operator, quantum mechanical operator for the momentum operator on psi. Okay, and this will be, you can show by, if you put this particular form of the wave function, you can show that minus I h cross. Now, gradient if for those who are not familiar with gradient, I will just put the expression for the gradient operator. Gradient is equal to I times dou by dou x plus j times dou by dou y plus k times dou by dou z. Okay, so that is the gradient operator. Okay, it's a three-dimensional version of the derivative operator. Okay, so if you take this gradient and operate it on this particular on psi of r. Okay, so if I take a gradient of a e to the I k dot r. Okay, you can show it again, it is fairly elementary, but I will not do it in detail. You can show that this is exactly equal to h cross k vector times a e to the I k dot r. Okay. So, what that implies? This implies that the momentum, the eigenvalue of momentum is equal to h cross k. Okay. So, you see that that this constant that is multiplying the wave function is nothing but the eigenvalue, and that is equal to the momentum. So, the momentum eigenvalue is equal to h cross k for a travelling wave in 3 dimensions, and this is again seen in elementary books in quantum mechanics. Okay. So, the point is that this sort of expression e to the I k dot r represents a travelling wave in 3 dimensions. It is a wave that is travelling along the direction of k, because it has momentum of h cross k, it is travelling along. So, k gives direction of wave, okay. And now this will actually be fairly useful to analyze the Bragg scattering. Now, before I do that, I just want to introduce the concept of a reciprocal lattice vector. Okay. Now, to do this, we will start with the following way. So if we have a lattice, okay, let me start with a Q. Okay, and we take some arbitrary vector r from one lattice point to another. Okay, we can write this as let me write it as n1 a plus n2 b Okay, so you can write it in this form. Okay. So, this is called a lattice translation vector. Now, we define a reciprocal lattice. So, we define something called a reciprocal lattice. Okay. And for now, let me consider orthorhombic system. Again, for simplicity, we will just consider the orthorhombic system, and so in other words, alpha equal to beta equal to gamma equal to 90 degrees. So, now imagine a lattice and let me also consider a primitive lattice. for now I will consider a primitive lattice. So initially I will start with orthorhombic system and a primitive lattice, okay. And now you imagine a lattice, okay, which is given by translation vectors. I think I want to change my notation a little bit. Instead of calling it A, B, C, okay, I will call it A1, A2 and A3. Okay, so I am just changing the notation, okay, into A, from A, B, C into A1, A2, A3, okay. And this is I am just calling my lattice translation vectors as A1, A2 and A3 instead of A, B, C, okay, because I want to use the B for the reciprocal lattice. So, reciprocal lattice is given a general translation vector in this reciprocal lattice, okay, is given by M1 into M3 into B3, where B1 in this particular case equal to 2 pi by A1. A1 is the magnitude of A1 into y hat, B2 is equal to 2 pi by A2 into j hat, and B3 equal to 2 pi by A3 into k hat. Okay, so I'm just doing this. I'll explain why this is useful. Okay, and just to emphasize again, A1 is equal to A I or A1 I, A2 is equal to A2 j, and A3 is equal to A3 k. Okay, so the A3 without the vector sign represents the magnitude of A3. Similarly, A2 without the vector sign represents the magnitude of A2, and A1 without the vector sign represents the magnitude of A1. Okay. So these are the reciprocal lattice vectors. Okay. So this is a general translation in the reciprocal lattice, and what you can see is that if I take e to the I k dot r, so if I take e to the I k dot r, okay, so this looks like a travelling wave. Only thing I have taken k to be a reciprocal lattice translation vector and r to be a lattice translation vector. So this is a, so k is a reciprocal lattice translation vector, and we will see what happens when you do this. So e to the I k dot r, okay, so equal to what? Okay, so equal to, what is this equal to? Okay, so let's take e to the I k dot r. So we see that e to the I, now k has m1. Okay, m1, m2, m3 are integers, just as n1, n2 and n3 are integers. They can be anything from minus infinity to plus infinity, but they have to be integers. Okay. So m1 into b1, b1 is 2 pi by a1 into I into a, and you take k dot r, then you have to take m1 b1 into n1 a1. Okay, and again using a1 as a1 I, okay, and substituting this for b1, what you will get is the following. You will get e to the I So, k dot r will have the first you will have n1, a1, m1, and for b1 I will put 2 pi by a1. Okay. And you have two other terms. I won't bother about it. Okay. So, let us just look at this first term. So, this is e to the I, and n1 into m1 is a constant, a1 will cancel, okay, and so you just have n1 m1 into 2 pi, okay, and whenever you have an integer, n into m is an integer, so this is just equal to 1, even you have other terms, okay, and any e to the I 2 pi into an integer is just 1. Okay, so the product of so this term will just give 1, and similarly the y and z terms will also give 1. Okay, so that is the property of this reciprocal lattice translation vector, that e to the I k dot r equal to 1 if r is in Bragg lattice and k is in reciprocal lattice. Okay. Now, I took this for the case, okay, so this can be generalized for non-primitive, basically all 14 Bragg lattices. Okay. So just as you have a Bragg lattice, so for each of the 14 Bragg lattices you have a reciprocal lattice, okay, which right now is just another lattice with some different parameters, okay, and this actually turns out to be very important in both in X-ray diffraction and in the band theory of solids. Okay. So, I will conclude this this third lecture of week 8 here. In the next lecture we will look at more details of X-ray diffraction. Thank you.